Send it all.
Okay. I guess that's on now. Thanks.
Our last speaker for today is Steve Roberts from Oxford University, and he will be talking about Bayesian Gaussian process models.
Okay. So thanks very much. And the ultimate application of this is actually going to be on some, as we'll see, some weather sensor networks sitting in the middle of the Solent. After Chris's comment about the excellent idea of getting the PhD student to work and have a desk where the data is recorded, I think Michael Osborne, who's at the back here, will get you a desk on a weather station in the middle of the Solent, which I think will be very good. Now, one of the things which you'll immediately notice, I put myself second author here. The lion's share of the innovative ideas in this have gone to Mike. I've prepared an alternative title slide that looks like that. So if anybody does have any very detailed questions, please do ask Mike over a glass of wine a little bit later on. So we're going to be having a look at Gaussian process models, but in particular, just want to put it really in the context. And I sort of really maybe ought to make this bold, computation efficient sequential Bayesian inference, because our interest is in real-time monitoring, very much like the talk we've just heard and a couple of other talks that we've had over the last 48 hours. And that really precludes a lot of computational time in many, many scenarios. So computation efficiency is really quite important. Unfortunately, as with all real-world scenarios, we have extraordinarily noisy data. It can go missing, as we'll see a lot in the examples. And hitherto, our research in this area is really concentrated on two major areas. Well, firstly is the classic sort of approach of state space modeling and the Bayesian varieties thereof, as very nicely expounded by the previous speaker, actually. Fortunately, I'm going to be talking about this, otherwise there'd be a very similar sort of talk to the previous one. And the Gaussian process models are something that we've come to as a way of folding in quite a lot more Bayesian information to the sort of state space modeling that we were actually doing. But again, we need to worry a little bit about the computational realism. Now, what I certainly don't aim to do, especially at the end of the day, is go through endless mathematical details, especially in the GP literature, and as with all Bayesian inference, these are really very, very elegant, extraordinarily important, well covered in the literature, and if Chris gives me the tenor, you can go and buy his book and Carl Rasmussen's book on Gaussian processes and learn pretty much all about the mathematics of them.
It's actually available online.
Actually available online, but I do get a small commission for introducing it. I don't actually have a large picture of it, but anyway. Okay, so why Bayesian? Why do we often stand here and beat this kind of Bayesian drum? And certainly from a perspective of spending a long time working in very real data processing, from biomedicine through to weather prediction, through to finance, through to a whole range of sort of mobile robotics and so on, uncertainty at all levels of inference really, really rears its head again and again and again. Where there's just, you cannot believe the depths to which data can try and corrupt itself to screw your algorithms really badly. And Bayesian inference, at least in principle, is going to handle this, all this uncertainty at all levels. Also, we have the idea we can fuse information, subjective and objective, and one common theme of several talks over the last day has been the notion that if we do have knowledge, physical knowledge, such as in the last talk about the way different sensors gate information and affect one another, that is subjective domain, deep domain knowledge we ought to be able to inject into things. Imputation over missing values, that's something we can do, whether we have sensor knockout or whether those missing values are future samples that we are yet to see. There is a single framework to deal with all this, and a very nice way of handling confidence risk and of course the ubiquitous problems of noise in all our sensors at all levels. So our objective in all of these things is a prediction or filtering problem. And we're given a stream of observed variables up to some time t, and we want to regress onto a set of outcome variables y at time t. And in the examples I'm going to show you, that outcome variable is the future time course of the observables. In other words, y at t is, for example, x of t plus h, where h is a time horizon. And the data in everything we look at is sadly missing. It's corrupted with unknown noise statistics. And in a multi-sensor environment, we may have capricious coupling between our sensors. That's really very nice because it means if one of them dies and we've learned that there is a coupling between sensor A and B and sensor B disappears, we can try and do a little bit better than just relying on our prior. So, but going fully multivariate in this, of course, introduces computational complexity. And as Chris rightly pointed out earlier, if you really then want to marginalize out over missing variables, it becomes a little bit more difficult. Though because we're working with Gaussian processes, everything is marginally Gaussian, so life is made a little bit more analytically tractable for us than if we were running, say, with a particle filter. So I'm not preparing to give an overview of Gaussian processes, really just to skim the surface of the flavour of the kind of things that we're interested in. I think the majority of people working in GPs are in the time series literature. So time series prediction, whereby we're trying to ride through regions of missing data. That could be a smoothing problem or the filtering problem. Performing Bayesian Monte Carlo. I should say time series prediction is something I'm going to talk about today. Performing Bayesian Monte Carlo, as we'll see, is something that rears its head. I was going to say ugly head, but I think it's an incredibly beautiful head, and it really improves the performance of our GPs for this particular application problem. Knock on from that, something we're very excited about is performing global optimization. And that's not something I'm going to talk about today, but I think is a very sort of exciting adventure out in GP world. So let's start by refreshing our memories as to why the humble but incredibly useful Gaussian is being used in this way. And it really comes about the fact that it's sort of the uber conjugate distribution. You can do pretty much anything you like with it, and you just get back another lovely Gaussian, and that means analyticity for the majority of your tasks. A Gaussian process in many ways is about trying to find a joint distribution, for example, across x1 and x2, as in this example here. If I look at just the marginal of x1, which is sort of a projection of this distribution down on this x1 axis, I have this big fat blue curve that really isn't telling me very much other than x1 is fairly uncertain. But if I then look at the conditional distribution, a p of x1 given a particular value of x2, in other words, I have now observed what the true value of x2 actually is in a sensor reading, that gives me this red curve here, and you can see in going from the blue to the red here, what in effect I've done is I've gone through a learning process. In other words, I've gone from a prior to a conditional, conditioned on some knowledge. And this sort of basic process, in many ways, for a simple, if it was non-Gaussian, is really a sort of a nice example of what the learning or inference process is all about. But for Gaussians in particular, this gives rise to a very straightforward framework in which we can do inference in a very natural, I think, very powerful way. So if we sort of take these conditional distributions, the marginal and the conditional here, and project them out in a slightly different way, which is to say here is x1 and here is x2, before we'd observed x2 lying at the value of -5, the error bars on x1 were rather large. In other words, they were in the region about standard deviation about plus or minus 4 on this diagram. So really quite a lot. And they were going to be centered around 0 as well. The moment we've observed x2 here, then this conditional distribution here has not only moved position, in other words, we have a location, but of course we're much more certain about the value of x1, and that is reflected by this mean here as a red solid line and these lovely pink error bars. So the moment we look at that as sort of a simple 2D case, we can then sort of consider extending that into a multidimensional system. That was for just 2 variables. Imagine now I had a covariance, a joint distribution, which was joint over 10 variables, enumerated from 1 through to 10. And let's say I'd actually observed data points at what was really going on at x2 and at x5 and at x9, for example. I can look at the conditional distribution of all the things I don't know, conditioned on those points that I have actually observed, and you end up with this sort of rather stepwise diagram like this. This is in effect a sort of a sampled curve And in principle, we can allow this notion to collapse onto an infinite number of dimensions, and we get a smooth continuous curve then. So Gaussian processes then in that limit give us distributions over functions, and that's a very, very powerful methodology. In a discrete sample set, what they actually do, if I'd extended this into hundreds or thousands, for example, I have distributions over unknown samples in a discretized time series. So we can see fairly straightforwardly how these Gaussian processes are going to enable us to perform inference. So there's certainly nothing new in what I've reviewed so far. But the kind of thing GPs are able to do is standard Bayes, for example, Bayesian expectation, fitting curves, drawing functions which explain the data, drawing functions which are drawn with a predictive distribution would explain the data and the uncertainty we have about where the data is not, takes into account noise on the data and so on. I should point out these schematics are of course schematic diagrams, but they're not drawn with sort of PowerPoint, they're actual results coming from a GP. So if we do have noisy data, we naturally are going to take that into account when we go through this sort of framework. So the two sort of major sort of applications we're interested in are tracking, where we're seeing time moving, say, from left to right, and we have some increasing error bars associated with where we no longer have observations. We observe the system here again and again and again and again, and you can see that causally that uncertainty is winding its way up to a point potentially where we find it unacceptable and we may need to do something about it. When we then force ourselves to do something about it, that leads us to do some kind of action which gathers information, and that's like active data harvesting, and I'll come back to that a little bit later. The other sort of thing we may be interested in, as well as the tracking issue, of course, is a prediction, and that's about observing a whole lot of data and making an inference, a distribution over the Gaussian process that explains what we've actually observed, but then actually extrapolating that out, for example, in the time series case, into times into the future. And of course, this is classic curve fitting with error bars. And again, Gaussian processes enable us to do this in a very, very nice way. So the beating heart of the Gaussian distribution is a covariance function. And to be a covariance function, there are various things that you need to be. For example, you need to have symmetry, you need to have positive semi-definiteness, and so on. But ultimately, all you need to be a valid covariance in the sample space. And what this covariance is really doing is explaining the correlation between two samples that are separated by some time delta t, but here I've referred to as t minus t primed. In order to be a valid covariance, all that you need to be is in the Fourier domain, you need to be a probability distribution. So the good old squared exponential that in effect is just a Gaussian distribution over the correlation dying away with distance in my time series is of course a Gaussian distribution in the Fourier domain. The Matern covariance, which is often used for more rough physical systems, is a student t distribution in the Fourier domain, and so on. So in many ways the point I'm trying to get across is we sort of take these forms in a very vanilla way and use them. And one of the powers of Gaussian processes, but also in some ways maybe a downside, is it does actually work very, very well using all of these sort of off-the-shelf functions. But of course a lot more can be gained if we calculate bespoke covariance functions that fits the physics of our system. And in a situation whereby we know we have some kind of stochastic differential equation or differential equation, then we can utilize that knowledge in order to build our own covariance. The covariance functions we're going to be building will naturally take into account known factors. It's to do with weather, in fact tide prediction in the Solent, and we know that tides happen roughly periodically and so on. So we can fold all of that in. But pretty much all these covariances have just parameterized by a couple of hyperparameters. And just referring, this is an amplitude, a height or length scale, h, and this is a time scale parameter that governs the information coupling length as you move two data points further and further apart. It's rather like a kind of a decay time in an autocorrelation sense. And those, of course, are things that are unknown. And more of that in just a moment. Let's have a little look what these look like. And here I've just done the sort of standard thing, which is in many, many books, and but I was going to say many papers. There's only one book, of course, that's worth buying. Sort of classic draws from a Gaussian process. And we have a nice smooth Gaussian process here, and we get this for the squared exponential. This is a draw from that GP. And as we change the time scale associated with the hyperparameters in, for example, this Matern covariance, we get a rougher paths as we change things. So these parameters, these hyperparameters, the height scale is going to define sort of, if you like, the amplitude of the resultant outcome function that I get. But very critically, the time scale parameter, this time here, is going to govern the roughness of the paths of the functions which I get. And in principle, I can get everything from a sort of a rough Brownian path through to a straight line by using Gaussian processes. So again, a really, really nice methodology which appears to be a real sort of catch-all. There is a little problem with that, which I shall come back to in just a moment. In a multivariate system, instead of just in effect curve fitting on sets of points which we know exist in time, we can imagine sets of points which exist in a two-dimensional index set. That index set is indexed by time along this axis and just by sensor label. We know in these examples what sensor is which, so we're not trying to solve the identification problem. And of course GPs can handle that at some computational cost, of course, but just as naturally as anything else. So the kind of flexibility we can incorporate into our covariances naturally takes into account periodicity, long-term drifts in the kind of weather data we're interested in. And if we have multiple sensors, we may, especially for things like tide tends to wash down a coast in a particular orientation, and down in the Solent it sort of comes from west to east. So sensors which are located more to the east are going to see those tide levels a little bit later on. So we may have indeed some kind of delays between these sensor measurements and so on, all of which we'd like to infer and learn about. Now each and every time we introduce extra complexity or knowledge into the covariance to explain the physics of what's happening, we're introducing hyperparameters. And hyperparameters are our friends in the sense that they buy us modeling flexibility, but they're really, really a nasty thing because we've actually got somehow to work with them in a computational framework. So we've got to do real-world computation, working out what these hyperparameters are all about. And the kind of thing that, of course, is problematic, if we just take the timescale one here, as we change this, we can dramatically alter the way in which we're explaining our data. Clearly, this blue curve and this magenta curve are on ludicrously wrong timescales, whereas this red curve is around about on the right timescale. So this looks like a sort of classic parameter optimization style problem, and indeed in some sense it could well be. So a lot of the time you use a sort of a Bayesian framework for doing the predictive distributions and doing the right thing with the parameters. But a lot of the time in Gaussian processes people are setting hyperparameters using, for example, maximum likelihood or maximum likelihood 2. That's absolutely fine. We find that gives enormous sensitivity, though, to the actual settings of these parameters. And a lot of the models we're interested in, with large number of hyperparameters, what we'd really like to be able to do is do the right Bayesian thing and integrate out that uncertainty and fold that into our predictive distributions. So certainly when I sort of first learned about Bayesian things from Adrian Smith, you know, it's like, why spend computational time optimizing? Never optimize, integrate. So being a good Bayesian, you integrate things out. And of course, that's what we'd like to do. The only trouble is, after all of these fabulous analytic solutions we get by everything being Gaussian, 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 and lovely and conjugate, the moment we scratch the surface of Gaussianity in the covariance and go to the hyperparameters, we have non-Gaussian integrals that we've got to perform in the hyperparameters of the Gaussian process. So from having a fabulously elegant everything's conjugate Gaussian, we sort of seem to have shot ourselves in the foot. So we could resort to maximum likelihood estimation, absolutely fine. We could also resort to something such as MCMC, but it's a non-Bayesian technique. I mean, it's a bit like speeding a bit on the motorway. We all do it. We know we shouldn't, but we all do it. So, you know, MCMC is essentially getting a big bag of samples and taking sample expectations and various things such as that. And that's not quite what we'd like to do in a Bayesian spirit. So one of the things that we've been looking at is sort of going back to inspired work by O'Hagan and others way back, I think in the 1980s. O'Hagan wrote his first paper on Bayes-Hermite quadrature, which is to say, if we're armed with a bunch of samples, we're actually looking at some marginal likelihood, a distribution over something we want to integrate out. We've got a handful of samples, we've got to integrate under that distribution. There are two things we can do. We can take buckets full of samples and do the integration that way. That would be a nice directed sampling approach like MCMC. Or, well, if we've just got samples, we know where they are and we know the value of the function at that point. In effect, we've just got another curve fitting problem. And so the whole sort of notion of Bayes-Hermite quadrature is to use a very small number of examples, fit a smooth likelihood surface, which we can then integrate under. So we can do the whole thing under a sort of a quadrature or cubature style approach in a multidimensional space. So what we're really interested in doing, if phi represents here the set of all our hyperparameters, what we really want to do is do these marginal integrals and get rid of our dependence on phi, not to set them to their maximum likelihood values. That, unfortunately, is easier said than done. However, the nice thing is the actual distribution, the sort of conditional distributions of all the things we're interested in, conditioned even on our hyperparameters, are conditionally Gaussian. And the nice thing about all of that is any linear operator on a Gaussian just gives me back another conditional or marginal or whatever under any linear transform that's Gaussian again. And lo and behold, of course, the integral itself is just another linear operator. And that means that if I've got some distribution about some sort of variable of interest x, and that's marginally Gaussian, then so it's joint Gaussian. It's joint Gaussian with its integral and any derivative and so on and so forth with it. So what that means is we don't actually need to use these samples, if you like, in order to fit the likelihood surface of the data under our hyperparameters. We can directly, and then integrate under that, we can jump directly to the integral, which of course is going to give us a little bit more, a bit more of a computational improvement as we go through. So here's a little sort of example of the kind of thing we're interested in. Maybe here, for example, this is the log likelihood of our observations given the hyperparameters and given any other kind of catch-all context that may be present in our model, such as the data can be modeled by a GP in the first place. This is the likelihood surface. We'll see this is a real sort of likelihood surface we get from one of our periodicity hyperparameters, and I'll show that as an example in a moment. What you see is that if we sort of sample this along a variety of points and use another Gaussian process to fit a regression curve through this, then we can very, very straightforwardly integrate under this. It's made even easier by the fact that the integral is conditionally Gaussian as well. So we can perform all of that analytically, but this is a horrible non-Gaussian likelihood surface, and multimodal as well. In order to integrate it out, we don't want to just take its mode and do like a Laplace or even a variational approximation to integrate out that uncertainty. The other nice thing we can do in all of the examples that we're showing here is we can explicitly work out what the gradient is, because we can work analytically what the gradient is. So at each one of these points here, we can also work out the value of the marginal, the conditional likelihood. We can also work out what the gradient is as well, very, very cheaply, because it's just fitting the numbers into the function at that particular point. And you can see that actually that really dramatically reduces the uncertainty in all that we're doing. So the use of gradients in Gaussian processes is not something new, but certainly for doing the sort of Bayes-Hermite quadrature, it hasn't received very much attention in the literature. So let's give you a sort of little example of this. Let's say we're trying to work out the periodicity of, based on, as we sequentially roll along through the data, of a set of simple a sine wave here with very simple periodicity, and we're given a series of data points, which are these black spots here. As we roll through the data, the Gaussian process isn't doing terribly well at all, and that's because it knows absolutely nothing about the intrinsic periodicity of this particular process. And to start with, we've got, if you like, samples, a very small number of samples in the hyperparameter governing the periodicity that are spread all over the place. The true value is 1, and we've got various sort of values here. Now what we can do is we can reweight those, again, because we can reweight them because we can evaluate what the conditional likelihood is of the data under that particular value. And we can reweight all of those, and of course the ones closest to the true value get weighted more and more. We begin to make a little bit better predictions as we go along, but still they're not absolutely fantastic. And of course what we would like to do, sorry, bit of a repeat there, is actually adjust the sample weights and positions. So very rapidly, in effect, what we're doing is utilizing this second GP that's running, integrating out our uncertainty, and readjusting where we're taking these samples. Very, very rapidly, we latch on to the periodicity after a fairly small number of samples. So that's just for the periodicity component of the covariance function. And of course, we can do this for all of our hyperparameters, be they to do with periodicity, length scale, time scale, and so on and so forth, of any esoteric covariance we might like to bring to bear. And certainly in the applications we've looked at, the performance increase over simply setting them to their maximum likelihood values is really very significant. Somebody want to ask a question? Yes.
At some point, are you integrating out using Bayesian, or are you optimizing?
We're ultimately integrating everything out entirely. Yeah. But
if log p is a Gaussian process, then but you have to integrate p, or
yes. Yeah. Sorry. There was another question.
I think I had the same question. I was just confused about if the log of p was a Gaussian process, but you want to do an integral with respect to p itself, then I'm not sure I understand exactly how the argument about the integral being a linear projection holds.
No, you're absolutely right.
Yeah. No,
the Gaussian process was actually
and it should
not on the log.
That should have been a p, not a log. Yeah, but it's been put in log space for the just because otherwise these would just be down at 0. It just makes it a bit more of an informative diagram then. So the integral is actually taking place over p of x given the hyperparameters. And yeah. Sorry, I should have said that's just for presentation. Okay. So when we have a look at the computational efficiency of this, we're obviously introducing another layer of computational work involved in all of these. One thing that we can do to try and cut down, if we sort of think about what's actually happening with a sort of vanilla Gaussian process, and as we increase time, as we go through, our time horizon starts ticking, we've observed, let's say, only 9 data points. In order to actually compute our predictive distribution over the 10th, we need to invert, in effect, a 10 by 10 covariance function. Okay, so the moment we've seen 1,000 data points, we need to invert 1,001 by 1,001, and so on and so forth. So these are getting larger and larger and larger. And of course, one thing that we can do is we can utilize measures of the information gain associated with each and every single data point. In principle, we could enumerate and evaluate every single data point and ask the question, are you significantly helping me to reduce the uncertainty in my predictive model? If you're not, you're out. In practice, we have a lag window which is longer than the time period we expect influence from the past to cover. But it is a heuristic window which we do need to apply. But of course then the Gaussian process saying, well, here are the new data points, new observations. I'm updating my model according to the standard GP equations, integrating out uncertainty in the hyperparameters. These are old observations, again, that are forming potentially sort of part of information that's in my covariance function. But there's also these old observations along here, which in this particular example, we can set a threshold on the information gain per sample, and we can brutally discard samples that are giving us less information than that threshold. That threshold is not something which we can infer or intuit a priori. If you told me we've got 5 milliseconds to make an inference, then that would set that threshold for me, because on average I'm not allowed to take longer than 5 milliseconds. If you say I can only work with 20 by 20 covariances to invert them, I'm doing something say on a mobile phone or some low processing power unit, then of course that informs the threshold as well. So this is a subjective threshold, but you can see in principle how very straightforwardly we can discard these old data points which are no longer informative to the problem, retaining those that are still potentially informative, giving us marginal information gain to future projections, and of course retaining very much the new observations up here. And this then sort of rolls forward through time, but in effect this time window here, the depth of observations from the past we're retaining is continuously adapting on a point-by-point basis according to the informativeness of points within that window. So, and that means that we're often dealing with much sparser systems than a full data set over a very long window. So the kind of computational speed that we get applying all of these systems, this is the number of samples associated with each hyperparameter in the system, or beg your pardon, this is the total number of hyperparameter samples. So as we go from 1 up to 1,000, we dramatically sort of increase the time taken for a standard computation. It goes as m squared. The number of data points retained, again, sort of loosely in terms of inverting, we're inverting this matrix. I mean, using the standard tricks to in effect make it just an n squared function, an order n squared as well. So computation time is very, very fast if we retain only a handful of potential points from the past. It may not be all 10, it may only be 2 or 3. It may even be only 1 if we've just got a first order Markov process. It'll latch onto that and just use it. If we retain more and more samples, very long range potential information, then of course in principle we can take a lot longer. So I still think in some issues there are computational issues for running Gaussian processes here. Certainly up at these upper ends here it runs way slower than equivalent state space model, but certainly in our opinion for this application gives really superior results. So let me explain a little bit about active data selection, because that's something I'll give a demonstration of in a moment. Imagine we've got a couple of tide height sensors here. This is sensor 1 and sensor 2, and what we're doing is we're busily sampling away, taking observations and so on. The Gaussian process can decide, because it's got predictive error bars, it can decide when the uncertainty has gone beyond an acceptable point. And again, this is something which we can set to say we don't want the uncertainty in any of our predictive distributions to go beyond a particular threshold, and we will then only actively ask the sensor for information when our predictions are going beyond that threshold. So active sensing, and of course we can do this in a multivariate system as well, very nicely, whereby if we have a lot of information coupling from sensor A to sensor B, we'll see that we don't need to sample sensor B very often, because most of the information regarding what's happening in B is already been observed in sensor A. And this takes place when we have phase lags in the tide, as we'll see in the demonstration. So let me tell you a little bit about the target application here. This is being applied to the BrambleMet network of weather sensors. This is a distributed sensor network. It's really a sort of vignette, a proof of concept on a real weather network out in the Solent, and we're sort of applying this in general to a whole variety, a very large number of distributed weather sensors which are distributed around the UK. And this is all part of a project called the Aladdin project, and I've put that down in the acknowledgements. So what we've got are a series of weather sensors located in the middle of the ocean, and if you look carefully, this is going to be where Mike Osborne's new desk is. So, and these are all logging data all the time. Now, rather annoyingly, they're logging data onto internal storage devices which are located at the sensors. Once in a while they do dump, however, so they're recording on a very fine time scale the true values of everything that's going on, which retrospectively we can go back and get, or at least people with boats can go and get for us. At the same time, they're also transmitting sparse, occasionally sampled information and putting it onto a website, which we can poll the website and we can extract information when that website refreshes. But that takes place in real time. In fact, that website is online. If I was online now, we can actually interrogate the Java applet that Alex Southampton wrote will interrogate these weather sensors in real time, but they don't change very often. It's a very boring demonstration. They can only change maybe once every 10 minutes, quarter of an hour. So we do have a very nice data set in the sense that it's real time but sparse, but we do have access to the underlying true data retrospectively by going and getting it off the disks which it's logged onto. And all of BrambleMet is used by Port of Southampton in order to control shipping. Southampton's and the Solent's amazingly busy, lots of people doing recreational sailing and so on and so forth. And awful tides and awful nasty rip currents. Anybody sails here will know how awful the rip current sort of out from the Isle of Wight between Hurst Castle and the Needles is. And so these weather sensors are really very, very important indeed. So let me show you the demonstration now, and hoping this works. Right, so here we've got a series of sensors which are located at Southampton, Bramblebank, Chichester Bar and Chichester Harbour here. These little windows here just represent the readings which are coming from these particular sensors. So in order to make it a slightly more interesting example, what I'm doing is I'm speeding it up by a factor of 3,600. So you'll see these samples coming in fairly rapidly at 1 second equals 1 hour. If I was to run it at real time, it's a pretty boring demonstration and we'd never get to our wine. So these are the samples you actually see from the web. Retrospectively, because this is now running offline, we can go back and we can actually say what was the true value of the tide actually at that sensor here. And you can see immediately that the values polled out that we actually have available to us that we see in real time actually often don't bear too much resemblance because they're highly quantized and not corrupted, but they're quantized versions of the original data, which is this black line down here. So what I'm going to do is I'm just going to put a Gaussian process. This Gaussian process is running sequentially. This is the real sort of output that comes from the GP. And it's already sort of inferring through this data here, but we've got full data so far. So the Gaussian process is working only with those red squares at the moment. So if I just run that, and you can see the data coming in a few times an hour in a real-time chronology, and I'm hoping very much that has it. Oh, thank goodness for that. In a moment, we're going to see a region of missing data. Okay, so here we've hit this first region of missing data, and you can see that the GP's never seen a full period yet, so it's actually not doing terribly well at predicting what's going on when we've got a block of missing data, and it just happened to come near the peak of this. We get another block of missing data that's coming a little bit later on, and we'll see that in this next missing data regime, the Gaussian process is actually doing significantly better compared to the first period here, because by this time it's actually learned a lot more about what's going on in the periodicity, and it's integrating out that uncertainty associated with that. So these are all dependent Gaussian processes. They're all coupled, so it's a sort of a four-dimensional predictive distribution, a 4D multivariate normal. We can do the same for considerably rougher signals, such as, for example, air temperature. And you can see that for the air temperature, again, we're not doing too badly, though here, where there's a big block of missing values here, again, there isn't such a simple periodicity here, so there's not nearly so much to go on. You see the predictive error bars are considerably larger here. One thing I can do, which is to just sort of pause that for a second, and instead of putting dependent GPs, put on independent ones. So these are now no longer looking at each other. You'll see that this prediction here, wide error bars though it is really very, very wide of the true value. But this is not taking into account the fact that actually these two air temperature sensors are slightly correlated with one another. They're not too far away, Bramblebank and Southampton Dockhead. So when we go to a dependent Gaussian process, although the prediction we make is not accurate in the sense that it's not tracking this unknown true value down here, it's considerably better than the dependent case. So we can then look to the second of these, so it won't be, it'll be the one on the top now. And what I'm doing here is exactly the same, but what we've got now are these true values. And now what we're doing is we're asking the Gaussian processes to request data from these sensors in an active sampling regime. And I'll run that forward again. I'll put on the Gaussian process prediction. This is a full multivariate system, and it's learning about the correlation between the sensors, and it's actively requesting data from the sensors now. So you can see it's actively requesting data from the sensors where its uncertainty gets beyond a pre-specified value. And you'll notice that already we've stopped sampling from Chichester Harbour. Actually, we probably shouldn't have done here, because you can see the ground truth and our prediction's a little bit off. But actually, the reason for that is Chichester Harbour lies to the east of these other sensor readings, and that means that as the tide sweeps in, there's a phase lag. That means we've seen pretty much what the tide's going to be by the time we've seen these more westerly sensor readings. And you'll see that apart from the odd sample on both of these two Chichester readings, sensors down here, we very rarely make samples, although we're actually making extremely good predictions that are almost exactly what the ground truth is. So active data sampling, very nice. The other thing we should note is that to start with, we sampled loads in all of our sensors, and gradually, even in these sensors out on the western end down here, we're sampling far more infrequently. We tend to sample more in regions of high curvature, as indeed there's lots of expectation that we should, and so on. So I could leave that running for quite a while, but I'm sure we all want to get to the drinks. So let me quickly sort of pop back to the slideshow here. So, and just sort of conclude. What we have been interested in doing is looking at a fully Bayesian Gaussian process model. And fully Bayesian means we try and integrate out the uncertainty in our hyperparameters rather than setting them at their maximum likelihood values. To do that, what we've done is use Bayes-Hermite quadrature, introducing another Gaussian process under which we can then integrate out that uncertainty in all of the hyperparameters. Certainly for the application we're interested in, the GPs have been a really good process model for looking at missing, correlated, delayed data and so on and so forth, and very importantly to perform active data selection. Certainly you can imagine in lots of situations, these kind of weather networks as well, actually polling a sensor, especially if it's a battery-powered weather sensor somewhere, if you ask it for data, it has to waste its battery power. So the less you ask for data, the better, the longer lifetime of your sensing network. So this is a classic bandwidth against information problem in sensor networks, which GPs seem to be particularly good at offering solutions to. So just like to acknowledge the Aladdin project, ourselves, Southampton, Bristol Imperial. Please do have a look at the website. There's this and various other bits there. EPSRC, who very kindly coughed up money for the Aladdin project. Alex, who wrote all the Java implementation, and Roman, who's another PhD in Oxford, who's been really keenly involved in the Gaussian process work with Mike. So thank you very much, and sorry if I've overrun. Please, questions.
Time for a couple of questions.
Can I ask something about the Bayes-Hermite quadrature? So it's true that for any particular value of the hyperparameters, the predictions are Gaussian. But we're integrating over the hyperparameters, you end up with a bunch of Gaussians, and you're not adding them, you're mixing them, right? Those predictions are actually a mixture of the ones from each hyperparameter. So you really can end up with something which is a non-Gaussian distribution. Is that actually what you're doing? Or I was kind of unclear from your statement whether you thought, I mean, one can work out a mean and a covariance predictive one, but that isn't really what this mixture is telling you.
Yeah. And I mean, Mike actually wrote the code, and I think him right of looking in the code that what you've got a predictive, you've got in effect a Gaussian integral underneath each sample.
Yeah, I mean, your final result is always a mixture of little Gaussians, one each associated with each sample.
And what you're doing is implicitly, in effect, you've got a weighting for that sample. So your integral is a weighted summation over those Gaussians. I mean, a standard Gaussian mixture integral. Yeah.
Alfred?
So the reason why it might work, this sampling approach, is that the number of hyperparameters is relatively small. Or I mean, I was wondering, just if it would be a high-dimensional space over which we try to integrate, then I would be very much worried.
Yeah. I mean, it's a very good question. It's an open question about the sort of conditional dependency between the hyperparameters as well. Of course, you can factor that distribution. You can treat it as a set of n, n hyperparameters, a set of n one-dimensional, and then that problem no longer really exists. I mean, in some ways, I'm not being cheeky throwing the question back and saying, I think we face this problem whenever we have a lot of parameters, be they parameters or hyperparameters, even if we're trying to optimize. We have a really horrendously complex likelihood surface in a high-dimensional space. And getting good solutions off that is always going to be very, very difficult. And this is no free lunch that somehow magically solves that problem. These problems still exist. However, if you take a Gaussian process model, apply it to our data in the formulation we've taken, and set hyperparameters by maximum likelihood rather than by integrating out, then the performance is degraded. Whether that transports to other people's application domains and other ways of formulating the covariance beyond what we've done is an open question. But
So I've asked Tony about the Bayesian Hermite quadrature, and he says it really works only in the domain where you've got about 6 or 7 parameters, and Carl and Zubin have experience of that as well. If you go to more parameters than that, it's pointless because high dimensional sampling methods are better. And if you go to less, then standard one-dimensional quadratures are quicker. So he said, because you wonder why there isn't more on it, because it's a really interesting paper. And he said that's the sort of reason, because there's this narrow domain of only, it's not super high dimensional and not super low dimensional, where you really get benefit from the Hermite.
there are two counters to that. One, I think by luck rather than judgment, we happen to sit inside that domain.
Yeah, precisely.
And I'm not trying to be overly humble on behalf of myself or Mike or anything to say it works very well for our application, and therefore if the glove fits, we wear it. But it is no great solution to absolutely everything. The second point that I would make is actually judicious use of derivative and or second derivative information, which is not commonly used in the literature for this kind of process. Now we know that has a profound, in fact, in several instances, it's actually better if you're asked, do you want the derivative or the function? It's better to say, I'll have the derivative, please, because that actually tightens your uncertainty way better and gives you better integrals. So. And I'm not aware of very much work that's explored those avenues in the sort of Gauss cubature literature at all. So that may not be, again, a final solution, but I think it is a compounding factor to improvements in our results.
Well, there might be a case where you actually know the analytical answer, maybe something high dimensional where Laplace might be okay, and you could just try it and see if you get the same.
I think that's a very good answer. I mean, it would be nice to empirically look at this over a very wide, maybe a larger sort of class of problems, but also sort of theoretically to look at this in a different sort of light. I mean, I would sort of point out that one of the things I haven't spoken about is the optimization, which really sets optimization as a set of decision problems, a bit like this sort of sampling in this hyperparameter space, where should I go to sample in order to get me most information about the likely maximum or minimum of my function. And that process, again in moderate dimensional space, really outperforms all traditional global optimization procedures. So I think there's lots of interesting work in these areas to be done.
There was one more question.
Yeah, so on the second layer of Gaussian process, which is used to model the likelihood, so you're saying something about, by using Gaussian process in that, you're saying you have some expectation that it's smooth, etc.
Yeah. Yeah. Yes.
But isn't there a problem that you can't say anything about positivity?
Yeah. I really think that's a big problem. And I mean, this is sort of a classic problem that dogs that whole sort of Bayes-Hermite literature as well. You're quite right, unless you go into the log space and actually do, but then you don't get the nice analytic sort of conditional Gaussian distribution. You're absolutely right. We don't observe, I mean, this is not an answer really, a profound one. We don't observe that we get negative values. But that's not really a good enough answer. But it doesn't hit us in practice. But you're absolutely right. And I think, again, more work needs to be done to retain the analytic side potentially, but try and solve some of those more profound issues. Yeah.
So I don't completely understand that method, but you're allowed to evaluate this function and its derivative wherever you want, I guess, in order to compute it.
Yep.
So can't you place those points in points which will keep you positive because you've got the derivative and it will sort of take you away from
I mean the function itself is always positive because I mean it's a likelihood function, so it's bounded below by 0.
I know, but you can't use that to help you because if you can choose the data and it's flattening out.
It's a very nice point. I would hazard a guess that you can judiciously choose things, but it may not sort of satisfy somebody who says, how do you know that between these 2 points that are positive, you haven't got a wiggle that goes down here below the 0? And that's a very valid criticism. And I think that's an excellent suggestion, but certainly need to continue a lot more work on that.
There was one more question.
In the active data selection, what happens if your model is terribly wrong? Let's say it's linear, then you never gain information, or it's nearly linear, so you would never sample. Does that happen, or? Yeah,
well, I mean, in this particular application, for sort of demonstration, we don't have a safety critical problem, but it's all about sort of expected loss. There comes a point when you haven't sampled. I mean, what you really need is a kind of fault or changing model. If you believe really strongly and you have lots of profound evidence that your system, the underlying dynamics are normal, so to sort of coin Chris's phrase, you're in a normal situation and there's not sort of novelty or abnormality, then life is fairly well okay. But if there's a chance that you could have moved into an abnormal system, the dynamics could have changed, then of course you're going to be not sampling and simply making predictions off in effect your normal dynamics. So in practice that's got round by actually taking a sample once in a while to check that you're still working okay in normality. But that sample has a cost, potentially a financial or timing cost, and that must be balanced against the probability that you believe that your dynamic model has veered from normality. So this is about a sort of cost-benefit trade-off. And these are sort of subjective thresholds which need to be, in effect, chosen according to the design of a particular application. But yeah, very, very good point.
Let's thank the speakers again.